Okay, we've got the shell theory for atomic physics and the Tableau formulation that simplifies that a great deal. So we're going to study that using the simplest model, which will be the U3 model of the shell of hydrogen, well, not hydrogen, but actually a carbon, and the P3 shell, that's 3 electrons together, coupled in Coulomb, whatever holds the atom together, and analyzing that using the Tableau analysis that we've been developing in the last couple of lectures. So I want to first of all go over just how U3 relates to the triplet of P orbitals, and the basic idea of the commutation relations and the elementary operators that help us do that. And we've already been through the P squared orbital states, the sextet and the triplet, and I want to go through it just using the elementary operators to get matrix elements by a very simple means, and review that. We already did the diagonalizing transform for this problem. We're going to actually use it today to make a check on what we do with the elementary operators. And then finally, there's this formula I call the jawbone formula that we discovered quite a long time ago that helps us make it possible to do a unitary theory of atoms, of nuclei, and the real challenge is the nuclear spin states of polyatomic molecules, but we're taking it one step at a time here. Okay, so a few more links here, and I should also point out that we really do need to, well, I don't have it up front here, I guess.
It's on the other one.
The links now. Oh, you've got it on there, good.
Well, I believe it's on the follow-up pages.
Okay.
On that other computer.
The those old papers, right?
Yes.
You thing number 3 of it. Okay, so here's the start of it right here, and let's keep these guys in sync because we have to compare a number of things, and some of the screens get pretty crowded by getting close to the edges. The basic elementary operator that we talk about when we were talking about the P operators, P12 times P21, typical product at the top here, but this one shows better. This product right here, E12 and 21, giving 1, 1. Remember that starts out really simple with Dirac notation, basic idea of the knuckle-to-knuckle product. That's an elementary operator in Dirac's notation, number 1, 2. And then the product of this with a 2, 1 gives me 1, 1. So that's this statement right here. Or, for example, this one, that would be written this way in Dirac notation. That gives 1, 2.
Dr. Hanna?
This is the basic formula for that, yes.
I think if you follow that notation, there's a typo in that matrix, E33.
The E33, oh yes, thank you. That's 3, 1, yeah. Anyway, the idea was, or else I'd let it 3, 3 and have the 1 sitting right here, yeah. What I was trying to say, there are 9 of these things. And,
Okay.
this is the last one if I put the 1 in the right place. Thank you for the typo. In any case, this generalizes when you're talking about Lie algebra. And that's what we are talking about here as we use the elementary operators to build the commutation relations. So this little guy right here is the first thing that you often get if you open up a book on Lie algebras or Lie groups. And that is the elementary operator JK with PQ, and a commutator would give me 2 elementary multiplications, one of them with a minus sign. So the proof of this is just to write out this commutator right here, and then notice that you get a delta Kp right here. That's the first term, and then minus the one with Qj. And so you're getting two elementary operators back again from a commutator. Anyway, this is very important for Lie algebra. Lie algebra is essentially an algebra of commutators. And we've seen a little bit of that already. Now, what we need to do is relate these to the boson creation and destruction operators. And this is the standard notation for quantum mechanics. But when it comes to actually doing the mathematics of them, if you have to write these things a lot, you definitely want to, particularly if it's the creation operator that you'll be writing the most, then you make the creation operator, that's this one, just be an A, and have a subscript if it's a multidimensional problem. And then the destruction operator has a little hat over it, sort of the death hat, I guess you could call it, because it's the destroyer now, where the one without anything was the destroyer before. And also, we don't use bold notation usually for the stuff that we're going to be writing here. So the basic idea is to make a definition for the elementary operators in terms of them. So first thing is to prove that that's indeed what you want, because the elementary operators really start with Dirac's orthonormality relationships. So if we're using creation operators, and this is the old standard notation, or destruction operators, but now looking from the left, their creation when they work on the left-hand side, these are conjugates of each other. That's understood in any of the modern notation for quantum mechanics. But the deal is that these vectors, defined this way with creation operators, makes a unit matrix. If you use these kets in an array, 1, 1 through 3, 1, that looks like that. And the proof of that is fairly easily seen. It's just based on the commutation relation that you get when we first did harmonic oscillators, just one-dimensional, but certainly with two-dimensional, where you have a commutation between the dimensions, and that's what this delta is making right here. And here's the shorthand notation for that. In any case, what that boils down to is the delta jk, and then this is delta jk times the vacuum probability. And it's assumed that the vacuum probability amplitude is 1. So that's how the creation destruction operators get their way into the group theory of matrices that we're going to be doing here in some detail. Now, once you have this, what about if you have more than one particle? And we assume that you do because of these numbers 1, 2, 3, and 4 here. The way I like to write this is to keep the particle numbers separate, because remember, we want to do this Mach thing where we move states from particle to particle, or else move particles from state to state. So particle A, particle B, and so on, they're going to be labels which, if they're identical electrons, are kind of silly because we're not supposed to be able to label the electrons. But if the electrons have spins, that's kind of a start in labeling them, and that's what you need in order to really get this thing to make sense. But in any case, we're going to use an uppercase letter for the elementary operator jk, where you have summed over all of the particles that you have, and we're going to start off having 2 electrons and go to having 3 in the discussions we do today here. So this is pretty much the basic idea of what we can do or not do. This n-particle commutation relation only works, that is, it will be just like the one for a single particle if the A's and B's and the A's and C's and the B's and C's, all of the things that represent a different particle all of those guys have to commute. So we have to get 0 for all the commutators. The only commutator that survives is the same dimension with the same particle, the same state with the same particle. Those are the only things that have a commutation that's not 0. So that has to be said, I think. And it's not made clear enough in many of the texts that describe this. So this is just a summary right here of this, and here we are just checking that the elementary operator that was just a single set of boson operators also obeys the commutation relation, the general commutation relation for unitary Lie algebra. All right, that's the bookkeeping that has to be said, and now we're already a third through the lecture, so this is not going to be a tough day, right? Well, there's some stuff coming here that is a little bit curious, but I think it's more fun than what I've just been describing. So one of the things that you have to notice is that to make this stuff work, we're mostly going to be writing using the tableaus the matrix representation of the elementary operator 1, 2, then 2, 3, then 3, 4. If we go that far, we won't today. We'll just be dealing with 3 things. But the ones that have just a single jump, so to speak, from 1 to 2, that's difference of 1, okay? To get an operator that goes 2 jumps, that is 1 all the way to 3, we'll need to be making a commutator of a 1, 2 with a 2, 3. So just pointing that out to start with. And also, what I want to discuss is we did a good deal of time worrying about the diagonalizing transform for states that were based on symmetry and anti-symmetry of various kinds. We're going to go through that again. So let's just take a look at some sample matrix elements, just using the symmetrized states. And there are 6 of those. Symmetrized 1, 1, symmetrized 2, 2, and symmetrized 3, 3. Well, they're already symmetrized just in their primitive form. But then 1, 2 really means 1, 2 plus 2, 1 normalized. That's 1, 2 plus 2, 1 divided by the square root of 2. And the same thing for 1, 3, and the same thing for 2, 3. But when you're done, you have 6 orthogonal states to work with, and that's an irreducible representation basis for U3 linear algebra, Lie algebra. And we're looking now at the operator destroy a 1, create a 2, which is the conjugate of the operator that destroys the 2 and creates a 1. So 1 does, this operator without the dagger would undo what this one had done. And this one right here, 1, 2, is the dagger of 2, 1. So whatever I get over here should be a transposed conjugate, and no worry about conjugate. Everything's going to be real today. So it's just the transpose. So anyway, let's point out, first of all, that the elementary operator 1, 1, which is the sum of the elementary operator 1, 1a and 1, 1b, all that's doing is counting the number of 1s. This is the good old A1 dagger A1, but we've taken the dagger away and have just write the thing as A and A bar. So what this thing does is count the 1s, and then this one counts them again for the B particle. So it's 1 for each. That gives 2. Okay, so that's our 1 plus 1 equal 2 law right off the bat there. So these diagonal operators, E1, 1, E2, 2, E3, 3, that's all we've got for U3. They're counters, that's all they are. And we'll make that point again as we restudy the irreducible tensor operators that we've already looked at a couple of times. Now, destroy a 1 and create a 2. Okay? Well, that's going to give me a tableau that has a 1 replaced by 2. And generally, we write the tableaus in lexical order, because we've got both orders in there. This thing, when it has different numbers in there, has to be the sum of one and then the flip of that. And then normalize, so that involves a square root of 2. So what happens here is the E1 to 2 goes ahead and does its job on particle A, and then this one comes along and it does it on its job on particle B. So here the A got changed from 1 to 2, and here the B got changed to 1 to 2. So we have 2, 1 plus 1, 2. That's a symmetrized state, but it's not normalized. It's normalized with a square root of 2. So the matrix element for this transformation is going to be the square root of 2.
Dr. Harter?
And that is, that's our first product. And if you get that product, you get pretty much everything else we're going to do here. Yeah.
So, if I would have had a minus between that state, I would have written the tableau as 1, 2 in a vertical way, right?
The minus between these guys is a different operator entirely. That's going to be one of our tensor operators, but right now we're just working with the elementary operators out of which tensor operators are made.
So
I don't know if that's helping.
Yeah, so I'm just asking, so like the way that you wrote the John tableau in that bracket, in that ket bracket, in
Yes.
that ket, is a symmetric state,
Right.
right? If you have
If you
written
put
like
a
a
minus,
vertical,
if you put a minus there, that would have been a vertical.
that's anti-symmetric.
Yeah. And in this case, 0 is what it would be,
Okay.
right?
Because those are symmetry operators, right?
Yeah.
You won't do
That's
anything.
kind of what they are. They're
Yeah.
testing the symmetry by destroying a 1 and creating a 2, right?
So, okay.
Right.
Then you're testing the symmetry by operating those
Yes.
symmetry operators. And
Yes.
you're really knowing that you're getting that information from the state.
That's right. Yeah.
Oh.
And encoding it in a matrix. You see, this square root of 2 is 1, 1 gets hurt by that to change into that, right?
Oh, okay.
Does that make sense?
Yeah, it does make complete.
Yeah.
It's like if I'm just like testing like the states and see like what they tell me by kicking them or something like that.
Yeah.
That's why
We
I
got
see
a
the
couple of
operator.
other tests here that are not as obvious that I should mention, but let's keep up with our screens here so we can make comparisons. I'll stop at this screen right here, and this one, of course, is just showing you where the matrix element is that we're interested in. This is the next stop right here. Okay, I'm going to do a destroy a 1 and create a 2. Okay, so when I do that, it's the same deal here. I got to destroy a 1, create a 2 for particle A, destroy a 1, create a 2 for particle B, and so forth. However many particles you have, and we really have 3 here. That's what we're thinking of doing later. But right now, it's a subgroup of U3. We're working on a subgroup of U3 called U2. But result here, you see, is I started out with a state that was symmetrized and normalized. Okay? So when I go do this, what I get is 2 of these. Then times the normalization 1 over the square root of 2. So the matrix element for this one is also square root of 2. That's this square root of 2. These are very different. Right? One of them sort of starting out with something and the other one's ending with it. Right? Those are the 2 Tableau matrix elements that are really distinct in this Tableau business, as you'll see later. And that's what the jawbone formula is all about. But we'll get to that. Now, here's another one that's kind of interesting. I got a 1, 3 here. This is U3, so let's get 3 going here. And I'm going to still use the same 2, 1 operator. So I'm going to finish this matrix pretty quickly here. So what I do with my 2 1s is particle A, particle B, working on these things. That gives me this, still with a square root of 2. Okay? Started out normalized, ends normalized. This one has a 1. Okay? So these are 3 very different cases, and that's about it. There's still one that gives 0 here, but that's another story entirely. E2, 1 here, well, there are no 1s up there, right? So there's nothing to destroy. It's automatically 0. Okay. All right. See if there's anything else. This one should have been circled to indicate that 1 that's down in the very lower portion. Now, this matrix is the transpose of that matrix, as you can see. Okay, let's go ahead on this one to the end here. That's the 1 circled properly. And then here's the 0. Okay. So don't expect these matrices to be non-singular, right? There's lots of times you destroy something that can't be destroyed. So you end up with a whole 0 row. That's the business. That's the way Lie algebras are. These guys pop up. Now 2, 3. I leave this one sort of as an exercise, but you can see the form of these matrices is pretty much the same. It's going to be 2 square roots of 2 and 1, 1 as you go through looking at all of the elementary operators. And as we've pointed out already, there are 9 of those, right? This is U3, it's a big group. Okay, give Nobel Prize, right? Got to respect it. I mean, why? I don't know. But let's just keep going here and make some use of this. As I said before, you do need to worry about going 2 jumps. Okay, 1, 3, for example. Well, 1, 3 is equal to, and this is something pretty easy to check, a commutator of 1, 2, and 2, 3. Now, remember when we were doing permutations? When we were doing permutations, I could get the permutation 1, 3 bicycle by doing a 1, 2, 2, 3, except that it wouldn't produce for me. If I did a 1, 2, 1, 3, I would get a tricycle, but if I do a 1, 2, and then 2 to 3, I get a permutation to work that way. No minus signs involved in that. But this is what we got to deal with if we're going to do the Lie algebras with these elementary operators. Work on the unitary side, not the permutation side. So here's a typical matrix element. You can see what I had to do here. Okay, I had to first do the 2, 3. It's the thing on the right facing this symmetrized state of 1, 3s. Okay, so it's going to destroy a 3 if you can find it, and create a 2. And let me see if it looks like. Oh no, I haven't done it yet. I have to include this guy in this calculation. So E2, 3, E1, 2 is going to go to work on this thing, and I get nothing from that because this one can't find any 2s today, so it's out of business, goes on vacation. But this one goes to work, okay? The 3 is created to 2 for particle A, and it is also done for particle B. Didn't leave that complete exposed nomenclature, but I think you see that. And then I finally get at the very end here to destroy a 2 and create a 1, and do it on, because this one has particle A and particle B in there, so wherever you find a 2 for your particle, you go to work. So I end up here with this. Again, that's 2 of those things. Over square root of 2 gives me a square root of 2. So this one's a little more long-winded because it's a jump 1 to 3, okay? It's 2 units, but fine, it works. Now this guy over here, okay, same deal. Now I'm doing it on 2, 3. Now both of these survive, so I have this thing minus this thing. They're equal, gone 0, okay? But E1, 3, not so. I end up here with, and it's the same deal here. I have to normalize this thing and then multiply by square root of 2, divide by square root of 2. Divide in order to get that, then the square root of 2 comes out in it. And that one right there was down at, actually I did leave out where that one ended up, okay. We got a 0, we get a 0 here with 1, 3 acting on 2, 3, that's this, okay, that's this 0 right here, and then finally we get another square root of 2 here when we're acting on 3, 3 with 1, 3. So I end up at 1, 3, starting at 3, 3. Okay, is that all clear? Is that sort of secretarial work that's involved in doing the Lie algebra of U3. Okay, and this is very bare bones. This should be, I think, in all Lie algebra. Whether it's in that one, I would check it. But this is rock bottom secretarial work for something that's considered to be advanced mathematics. It really is sort of almost childish. Now, what's not almost childish is the using of the projectors to obtain. Now, this goes back to lecture 21, page 13. So if you want to check on this again, you would just click on that guy on the screen. Now, if I go like that, it's not going to happen. But if you have a appropriate electronic device where you can click on that, you will get to page 13. I've checked that at least once, I think. Okay, so here remember what we did. This is a sort of review of the diagonalizing transform, where we were transforming, originally we were transforming a permutation group representation that commuted with this thing, the unitary group of representations. And this was a particular projector gotten from the permutations that we are claiming has waiting for us if we normalize. We got to normalize every column there, but each one of these columns became a participant. There's this one right there, and then this one right here goes and makes that one, and finally there's one guy down here that makes that. So that takes care of all of the columns. There's this guy and this guy to make 3 columns that are very simple, only a single one in each of them right at the center of the blocks and then the edges. So they're all symmetric states that we're talking about in the previous a few slides. But also along with the bargain comes the triplet, the anti-symmetric triplet. So we're already doing the atomic physics of 2p electrons. Symmetry combination, there are 3 ways to do that. And then there's the anti-symmetric combinations. I'm sorry, there's 6 ways to do this, and then there are only 3 ways to make it anti-symmetric. And so here is the anti-symmetric projector from a permutation analysis, and we're pulling off 3 linearly independent vectors. Okay, these guys not linearly independent of what we have. So that's a complete set right there. So this is a transformation matrix that's going to take the unitary raw matrices that we just calculated and turn them into irreducible representations of the unitary. And that's what's coming right here. So this is where I put that D-tran here on the right-hand side because it's column vectors, and so the kets are there, and the side that should be worked on by the D cross D U3 matrix has to hit this thing from this side, just to remind you of that little secretarial detail. So this is the product of, and there's the elementary matrix that does destroy a 2 and create a 1. Okay? Destroy a 2 and create a 1 just from a raw primitive product state takes 1, 2 into 1, 1. No worry about normalization. Or 2, 1 here. Okay? The 2 gets destroyed and again turns into 1, 1. And so forth, you see. Here I destroy 2 in something that had 2 of them and end up with just 1, 2. Okay? And so forth. So these are really easy but kind of useless matrix components. This thing by itself is just sitting there waiting for the transformation that's going to take it to heaven. So here's the T, and then here is going to be the T transpose. Right now I've only transposed the labels. We'll get around to trans. So this is not an easy, terribly easy test. I mean, it's not something you do in 1 minute. Okay. Now I figured out ways to make matrix on paper that's fairly convenient, but doing 3 large matrices, and this is not terribly large. I mean, it's 9 by 9, but It's not the little 2x2s and 3x3s we've been working with. So you end up here with a D cross DT product, which by itself is kind of useless. But when it combines with a transpose of this, we're hoping that it will produce for us, and there you go. So if I take this matrix, the green flips up to here, the sort of light blue cyan box there flips to a horizontal box right here, labeled appropriately, okay? 1, 1, 2, 2, 3, 3 for the horizontal guys, and then 1, 2, 1, 3, and 2, 3, symmetrized. There's your sextet right there, but we got a bargain today here. We've got the anti-symmetric 3 that came out of the last 3 columns, becoming the 3 rows here. So here is the similarity transformation that we want, and if you go ahead and work that out, you get this. And that's what we had for 1, 2. So you can see the Tableau algebra with creation and destruction operators for this particular simple example is really easy. We got these square roots of 2 and that 1 fairly easily. This is a way to check it, you might say, but there's some issues. What phases do I use for those guys there? This particular set of phases turns this one into a -1. And that deserves some more discussion. So we're going to be taking a different route to this fairly shortly here that solves that problem. Okay, that's all I think I'm going to say about just the basic P squared, the 2-particle U3 states, the sextet and the anti-symmetric triplet. And the anti-symmetric triplet kind of mirrors, and we're going to see what it means to mirror in this business, kind of mirrors the fundamental representation of this, which is the 3x3 1-particle defining representation of U3. That's probably the best way to describe it. It is the fundamental representation. But this guy here is the other one, and they come in pairs, these guys. Particles and antiparticles is one way to say it. We'll make more noise about that fairly shortly here. So, okay, elementary operators. Do they have anything to do with physics? It's fine to be doing mathematics off in the corner and not paying any attention to the physical world, but this has to stop. You're breathing nitrogen and it's got a P cube configuration that we're going to explore here. L = 1, atomic P shell, but I'm particularly interested in the U3 case of that. So let me show you what we have to do. And we've already done this. This course started with the A, B's, and C's, right? The spinors. First the unit operator, asymmetric plus diagonal, but the asymmetric minus diagonal we called the A or Z. And then there was the Y, which was anti-symmetric with imaginary. That was the C, the curly, complex, centrifugal Coriolis current-bearing son of a gun. And then finally a bilaterally symmetric B. Okay, so these matrices we've already seen. We've also seen their real plus imaginary and real minus imaginary combinations of those parameters, A, B, and C. Just B and C for that, and then this one remains the same. So here are two nilpotent operators. They're very important for our Lie algebra. But these are important also for the Lie algebra. Lie algebra of the spinors, as we've been working with. Okay, so this is the U2 generators. And as I promised you, we generalized that. And we have actually lots of references here to where we have it. This really comes out a number of ways. AMOP lecture 11, that's for our particular lecture right now, but there's some other places in text to get it. So the next step up from these guys are 3x3 matrices. The first 3 pretty much like these. These are rank 1 vector in that space. This is very much a rank 1, what we call a 3 vector in R3 and U3 space. So there's a set of matrices that belong to the generators of the of the U3 group. But they're combinations of elementary operators, all of them, because elementary operators are nothing but a zero matrix with a 1 in the ij place for Eij. Couldn't get much more elementary. But I would like you to notice that the commutativity of the U3 and U2 as well is exposed by this array. That is, matrices out here generally do not commute with anybody. This one least of all. Okay, the further you are from the center, the less you commute. But these guys all commute with each other. Okay? Not necessarily with other matrices, in fact probably not, but with each other. And that, remember, is the definition of what we call the rank. The rank was the maximal set of commuting observables, is the way to state it physically, right? So here they are. Thank you. That comes pretty easily. That's something that's fairly difficult to see with D3 group, right? At first, until you get used to the algebra. Okay. So, using these, we're going to build all of the matrix elements that we need. And the trick is to realize, actually, that these numbers sitting in these boxes, and that includes the normalizations that go with them. Each one of these vectors that's on a slant is a vector to be taken seriously, even if the slant is off diagonal, okay? And of course, if you're just off, way off diagonal, it's really obvious. You're all by yourself, kind of. But if you're just off the diagonal, then you get two of these, and note the orthonormality. They're both all normalized to square root of 2, okay? And notice that for this one is a 1, 1, 1 with 1 over the square root of 3. This one with the square root of 2, and this one with the square root of 6. 1 squared plus 2 squared plus 1 squared. That's the normalization that has to go in the radical, 6. Okay? So that makes it really easy to convert any sort of matrix we might want to represent in terms of dipole, quadrupole objects. And then there's, of course, the scalar always resides at the very bottom of this pyramid. Okay? Now, the condensed format for this is just to take all 5 of these and pile them together, because they don't use most of their space. Most of their space is filled with zeros, which are indicated by the dots. Here we use the space efficiently, so we're saving paper by putting this entire array accordion collapsed, and then its normalizations are shown off to the right. And this one too, it has its normalization. It doesn't need one for that because it doesn't use the 1, 3 or the 3, 1 component. Only the tensors here can find use for that component, and they do, just perfectly. So this is where you write the irreducible Racah tensors. There's someone given the name Racah, but the Wigner had thought of these too, and Fano and a bunch of other people that worked in the early days of atomic and molecular physics, but also quantum theory. This is just a Dirac notation for that, and it's these matrix elements right here that we're plotting in this table, but also in the array. And I use a shorthand for that. I used to write a parenthesis, rank k of the tensor, that's 2, 1, or 0, and then the various m values, which go from 1 to 3 in our elementary numbering system, but really they go from minus L to plus L if you're actually using m values there. Now I sometimes put little parentheses around that to indicate that I'm going to renumber the annoying 1, 0, minus 1 just as 1, 2, 3 in order to do our algebra, right? Easier to write one character and put a minus sign on the thing and figure out where it is. Just, it's in order, 1, 2, 3, 4, 5, 6, if you're doing U6, okay? So I hope that makes some sense here. And also, it's at this point where we actually plot the values of the commuting generators, the ones in the very center of this matrix, okay? And we plot it in 3 dimensions. There's a 1-axis, there's a 2-axis, and there's a 3-axis. So obviously this is actually a 3-dimensional triad, and you're looking down the 1, 1, 1 direction, and its projection onto a plane that consists just of, well, we're going to have on this axis the quadrupole matrix, and on this axis we're going to have the dipole matrix. Now the dipole goes from 1, there's the 1, okay, to 0, okay, 0 relative to this axis right here, the dipole axis, and that's a scale factor. This one has a scale factor of square root of 6. Those are just the numbers that are sitting outside there, okay? And then finally, the last number, -1, is down here. So -1, 0, and 1 accounts for our quantum vector. Those are the quantum states. Those are the M values, if you will, that will be recorded. And then sort of the M squared values are shown on this one. The square of this is a quadrupole. And the quadrupole has 2 1s, and you can see that here. This one and this one are just above what is 1 on this scale of square root of 6. Okay? And then the other one is a -2. So this distance here times 2 in the minus direction is the number 2 state. And then the number 3 state is here, and the number 1 state is here. So we're looking at this thing both as its dipole properties, 1, 0, -1, that's this, and then we're looking at it as its quadrupole eigenvalues, that's 1 and 1, 2 of them, and then -2 in the middle. Okay, so that gives you this relationship right here. The scalar one we haven't talked about, that's coming directly out of the board. That's the number operator right there. Okay, so in this 3-dimensional diagram, as I come to higher and higher planes, up to 1, 1, 1 direction, I keep getting the number operator to go up. But in the process, I'm making very complicated triangular polygons out in the various levels above the origin in the 1, 1, 1 direction. So that's the easy one. But here's the one where I have 1, 1 minus 3, 3. Now that turns out to be our orbital angular momentum z right there. Okay? And then this thing turns out to be a funny kind of QZZ, is what I call it. But you can see its angular designation, which is far more useful than the Cartesian one, giving us E11, minus 2 E22, minus 2 right there, and then E33 right there. So here are all the operators that commute with each other, mutually commuting. Not all commuting, only one of them does that. That's the unit operator right here. But the rank is 3. That's what you say, rank of Lie algebras, well known. Rank of finite groups, not so well known. But it's the same thing for a physicist. Mutually commuting set of observables. Okay? Is this making sense? Sure.
Did you say anything about Casimir operators yet?
We're trying to avoid, that's a whole nother thing I want to do. I want to do how the characters are eigenvalues of Casimir operators, but that's a story for another day. That's another approach to all of this. That is the first approach. But the first isn't always the most useful for making things easy. Okay, now the off-diagonal guys also need those. Okay, the obvious ones, the V1 sub 1, the vector angular momentum component positive 1. Well, it's just going to be square root of 2 times 1, 2 plus 2, 3. I'm talking about 1 plus 1 over here. I think that's right. Yeah, and this is a minus sign on this guy because I've got minus numbers right here. Okay, Now that vector right there is orthogonal to this vector up here. Remember that orthogonality is so powerful when we have to solve quickly to get some matrix in terms of these V operators. And then the minus one guy, he's on the other side here. No minus sign in front of this, but it's a difference, just like this one's a difference. It's just that this one is 1, 2 minus 2, 3. This is 2, 1 minus 3, 2, conjugate, or transpose, if you will. Okay? And then, at the very end of this, and this is the quadrupole, these are the 5 quadrupole components, taking out the top row here, okay, and written in terms of elementary operators. This one, in terms of 1, 3, and that's this one over here, 1, 3, okay? And then at the opposite end here is the opposite end right there, 3, 1, okay? Then these guys are differences where these guys are sums, okay? But this one has a minus sign in front of it and a plus sign, so this is an anti-symmetric pair. This is a symmetric pair for this guy. I do believe we've got that. Let's see, once. Well, it doesn't. It really isn't an issue because these are completely different operators than these. Both cases, I believe, we have. And I see I have left a typo. That shouldn't be there. The 2 minus 1 minus 1 should have this guy, but not that. Let's see if that goes away. No, it doesn't go away immediately. I thought I had corrected that. There it is. That's what it's supposed to be, and then it just didn't get transmitted to the rest of the page. But while we're here, let's remember the orthonormality of these things. It wouldn't make any sense if I had that typo. Okay, anything else we need to do before we actually use this stuff? Because you see, what you need to use this stuff is first that table right there that's at the very extreme right of the other screen, or at the extreme right of this one, okay? This is a condensed format, so we don't waste a lot of space putting zeros down on paper. And so that is this collection right here. There is the vector V1, V super 1, and then a Q sub-quantum number that is defined by these little numbers right here. That's 0, 1, 2, and then it doesn't say minus 1, minus 2. Looking at the subdiagonals, it just labels the superdiagonals. So that's all we're going to work with today, right there. But if you go to the D shell, L equal 2, then you got a 5 by 5 matrix, because there are 5 states in the fundamental representation of the D shell with a single electron. You've got 5 orbitals, angular momentum states. So here are all the tensors that go with it. You see it's very rich. It goes all the way up to 2 times its angular momentum. That is 4, so it has rank 4 tensors in it, as well as rank 3. So there's the octopole right there, and there's the hexadecapole right there. But then there's the quadrupole and the dipole right there. And then we don't bother putting the unit matrix on in this set of tables. So you won't find an additional thing here showing that part of it, where we have unit matrix. This would be a 5 by 5 unit matrix. This is a 7 by 7. Now we're talking about angular momentum total 3. This is the F shell. I was going to use these operators. And at the end of this talk today, I'll show you some of the complexity of the spectra that results from what we're going to do with this little baby right here. And it's pretty complicated for D, and of course these are the things that determine all the semiconductor properties of the middle of the periodic chart, made of things that have D electrons at work, right? So we owe our everything going on in this room to this one right here. But also a little bit, if you look at the bottom of the periodic chart, the lanthanides and the actinides, there's 2 rows down there that use F shells as their chemistry. And as we learned from our lecturer Ryan last week, these are created in neutron star collisions, apparently. along with gold and a bunch of other heavies like tungsten and platinum and all of those things that are heavy and rich in neutrons. Okay, so just to give you some feeling what it is we're doing here. Now, as far as these tables go, I have one scan here. I think it's easier to read on most computers than the one that's just mostly white and black. But eventually, I think what we need to do is write a program so you can make this matrix for any angular minimum. And the other tables that I am not showing you here are the ones that go cross shell. If you have a P shell and then you've got a D shell above that, you need a table of this kind of elementary operators for that as well, if you're going to play this game with the Lie groups. Okay, well, we're doing pretty well here. I think we can finish this up and still not take extra time today. I want to show a typical Tableau calculation and give you some feeling for what you would have done if you didn't have this thing I'm describing here, where you do all your calculation by CFP. Those are coefficients of fractional parentage. And they used to have big, thick books full of these things that you needed, in addition to the Rocca coefficient we haven't even discussed yet in this class. And the Clebsch-Gordons, we're using the Clebsch-Gordons to make our tables. And once you've done that, then you just proceed as though they weren't there. So I want to make a comparison between the two methods. Now there is one thing. If we're going to do the P shell, I would like to start just from the top and work down. You can do the other thing if you want to, but this is probably the most educationally provocative, I guess is the word. We're going to have as our start a tableau that looks like that. And the tableau allows us to have a symmetrized, but also anti-symmetrized, something that's called parasymmetrized state. So this is the state that we call the E state when we were dealing with the point group, D3. So this is the two-dimensional as far as permutation group goes. But if you recall, when it came time to do the unitary 3 group, the dimension of this representation, that's just the first of 8. This is the 8-fold way, the octet. And you know, we got to check it with the hook length formula, okay? A very quick way to see what's going on. Now the deal is, when we do orbital calculations with a tableau, the biggest atom in the entire universe is not going to have any more than 2 columns, because it has to be married, if we're going to make electrons be the active agent in our orbitals, it has to be anti-symmetric. That means that this tableau has to be married to the conjugate tableau, spin tableau, okay? And this particular one is showing a spin of 5 halves by having 5 spin-ups. And then the rest of it paired. Okay, so this is some monster shell, perhaps in something even more complicated than the actinides. But I just showed this picture here to get you used to what we still have to do, and this will be done in the next lecture, I hope. Show you how we marry these two and why we marry them and what's involved in the arithmetic of doing that. But the idea of the Pauli or Fermi-Dirac theorem that if you're dealing with half-integral spin, you are automatically dealing with particles whose overall permutation symmetry has to be anti-symmetric. So easy to state, so difficult to see why the hell that is true. And so far, as far as I can see, no one has been able to state a reason behind that that makes sense. I've given some reasons that don't quite make sense, and these are the kind of things Al likes to worry about, and he should. Everyone should. This is, you know, what are we doing with this thing that's so simple to state and so difficult to understand why it it exists. You see, it's really an important part of our life because we're all made out of fermion nucleons and fermion electrons. So, can't get rid of them. If you're only made of bosons, I guess you'd be called bozo, right? With a red nose. Anyway, here we're starting with the very highest orbital momentum. That means the lowest numbers. Remember how we number 1, 2, 3? That number goes up. 1, 2, 3 goes up. Well, the actual momentum that goes with it is going down. 1, 0, minus 1, right? So we're starting off here with the smallest numbers to make the highest angular momentum. And I've got a 1 here, a 1 here, that's 2, and then a 0. So I get 2 times 1 and a 0. 2 is 0, right? So I end up here with an L equal 2 state, and I really mean M equal 2 as well. Okay, so this is an L equal 2, but I'm going to from now on be labeling, I think, M equal 2 when I'm actually doing the arithmetic down on the lower portion here. Okay, so there it's stated. It's L equal 2, M equal 2 state. Its Fermi spin mate would look like that. So this is going to be a doublet. That's spin a half with a pairing that you can't see because they pair up and sort of disappear. So I'm left here with just spin up and spin down. Now that's the old spectroscopic notation. It makes sense because that's what you actually see. Apply a magnetic field to this level and you're going to see it split in two. So the naming, one of the rare cases where the naming really tells you something you're going to see in an experiment. But the way we're going to handle this thing is we're going to apply a lowering operator like you would do if you were doing quantum mechanics of a single particle. Or in this case we're dealing with 3 particles, but you would be able to do it with 2, I think. Just using standard things. Where the standardness breaks down is with 3, and that's what we're dealing with here. So after 3, it's tough work. And this is talking about 15 there, so that's well outside of this standard practice. So what I'm going to do is I'm going to use L minus, and we already saw what L minus was when we listed these operators. And let's just go ahead and do it again here on this thing. Down at the very bottom there, you'll see, and it's unfortunately in the chalk tray, but so let's just focus in on it so you can see where that is. I have, from using this and this is L plus, that's L minus. That's what you're seeing down there. E1, 2, and 2, 3 added up. That gives me right there L plus, and then L minus goes with the minus side of this thing. That's this one. That's a lowering operator. 2, 1 plus 3, 2. Okay, with a square root of 2, which is what's hanging outside of all of these angular momentum. Dipole-like vector quantities is what they are. Okay? So, that's what we're going to use. And the thing that we need to do that, the thing that is required to carry that out, is this crazy thing. Now, this is coming from that PHYS article we wrote in 1972. Ms. Patterson and I sort of cadged this together. We just had a way to describe all possible 2-column Young tableaus using the same notation that the hook length formulas that we've been talking about for dimension, kind of the same, okay? And the basic idea is the instructions for this are on the next page. You might just take a gander at that. There it is. There are your instructions, okay, for using this thing. Now we've already done a couple of them. All right, E2, 3 here. We actually didn't do that one, but we did do this one. E1, 2, 1, 2 gave us a square root of 2. That's the largest matrix element you're going to get out of either of these numbers here. Most of the time, you just get 1 for many of these, okay? But this is the crux. This is the cool thing about this using of tableaus that we need to know more about. As I say, it's something that's that works. It's catched together. So if you're a mathematical purist, and Brad is that some days, you would not like this. But, you know, take it for what it's worth. And that is, as you'll see, a lot. So when I apply L minus, I'm going to have to do an E21 and an E32 on that tableau. Okay? And the basic idea is you figure out which one of these cases do you have here, and proceed. Just destroy 1, create a 2, and destroy a 2, create a 3 for these combination. Okay? And that's the answer that comes for this one. So what we're doing now is we're working from the very highest state, which is highest on this axis, that determines the quadrupoleness of our thing. And we're going also out to the ends here of the dipole axis, which is right here. So all of these 8 states are going to make a matrix that describes what this particular D doublet does. And at the same time, we're going to be looking at a doublet P. And the doublet P that you get here, the 2P M equal 1 state, is simply orthonormal to this. And that's a quick shortcut to getting the other state that's going to show up in this. Now the one that's missing from P3 is the anti-symmetric triplet. Anti-symmetric singlet. The one that will be married to spin 3 halves. And that's a quartet. So there's a quartet waiting here. So we're not going to talk about that. We're going to talk about spin in the next lecture. But just the doublet states, there's a D and a P. That's 5 plus 3. There's 8 states. The 8-fold way is right here in nitrogen. You don't have to go to high energy physics to get the 8-fold way. Yeah.
So are the tableaus are stand-ins for irreducible representation?
Basis of irreducible representation.
Basis.
This is an irreducible representation of dimension 8.
Yes.
And these are the states that base it, the base states of it. Does that make sense?
Well, okay, so maybe we need another list that's saying how to take a tableau and associate it with a particular letter. A, E.
We kind of already have that because of these 3 guys here are giving me where I am in the 3 space of boson 1, boson 2, and boson 3, right?
Yeah.
Right? So we're already labeling all those quantum numbers. But somebody that does quark model would already say, of course, the 3 quarks, right?
Yeah.
I do the right combination of quarks and I used to remember where they all are. Neutron, proton, psi, 0 psi minus, and then we've got 4 guys here. I think one of those are the sigma particles, I think, and then there's a lambda particle that's sort of, and it's lonely, and they get in each other's hair and do all kinds of wonderful mixing at high energy. So the 8-fold way, which fit the standard nucleon resonances, was the start of Gelman's theory. And then his Nobel Prize comes when he goes for the totally symmetric, which we can't do here. We can't have a totally symmetric state in the P shell. We'll get one later in the D shell, but not here. But that was the one that gave omega minus, which was the plum.
Because I remember the last thing we were talking about is
the capital.
Some of them are A1. There's a certain number of A1s, A2s, and E's in a particular.
Using the notation for D3, right?
Yeah.
Well, that's behind the scenes here. This is definitely an E,
Okay.
right? If you're just talking permutation group.
Yeah.
Now you see the difference between a permutation tableau, which never had repeated numbers at all. You just had 1, 2, and 3 in some arrangement,
Oh,
right?
Yeah.
And there were only 2 arrangements
right.
because it was an E,
Yeah.
which we know is a doublet, right?
Yeah.
Here, I'm allowed to put ones copied in the symmetric part, but then the next one has to be something different from 1,
Oh.
right?
Yeah.
That's the rule for anti-symmetry, right? The columns act like they're anti-symmetric, even though when you look at them in detail, they aren't quite. They're para-anti-symmetric, which means almost anti-symmetric. Okay, so here's where we stand right now, and that's kind of where we're going to stop. I'm just going to. We don't have enough time to make much use of what we got, so the rest of this is just going to be showing a few things. First of all, I want to calculate some moments. Okay, so I'm going to actually calculate the multiple moments. That's quadrupole, dipole, and scalar. Scalar I kind of know already, that's 0. But maybe dipole would give us something, and maybe quadrupole would too. Anyway, I need these numbers right here in front of my elementary operators, which are counting number of ones, number of twos, and number of threes. So that's all there is to calculating matrix elements of actual physical operators. And what we're looking at right now, if we're going to talk about quadrupole or any sort of, we're looking at a possibility of some sort of transition strength, maybe, between the two doublets, D and P. And this is the P, and there's the D, so stick them in the matrix and go to work. And that's what the rest of this is, okay? I just go through here and I put these numbers from the table of tensor operators, which is sitting right there for our case, okay? And then I put the, let's see what else is here that's not showing. I've got a square root of 2 here. Anyway, yeah, that's because the 2 square roots give me 1/2. And then the rest of it is just the numbers that sit in that matrix and the things from the table.
Your range going down.
Anyway, only one of them lights up. Minus a square root of 3/2 comes up for quadrupole. Okay. Now what I'd like to show you is comparison. Okay, this is the minus square root of 3 that we get for the quadrupole. And that's what you got to do it. You got to do some Young tableaus and their matrix elements. Okay, I'm using that's the jawbone formula. Okay. Here's what you've got to do if you use the old-fashioned coefficient of fractional parentage. The coefficients of fractional parentage are these things. And they have to be laboriously tabulated in a big thick book. And then these are Rocca coefficients. You see, the problem with Clebsch-Gordon analysis is it's really great if you only have 2 things. But then if a third comes along, you have to decide, well, am I going to couple that guy first to the second one, or am I going to let the first one have that and the other one gets sloppy seconds? Then you have to have a transformation, which are these things, to transform between the 2 ways of coupling 1 and 2 and then 3, and coupling 1 and 3 and then 2, or coupling, what have I missed there? 2 and 3 and sticking 1 on last. There's all these different ways to couple, right? It's more like a dictatorship, okay, where you take your assistants just sort of randomly out of the crowd of your friends. This is a democracy, okay, compared to that, all right? So all of this, add all of this, get every one of these numbers, add them up, and if you're lucky and don't make a mistake, you get minus square root of 3 over 2. Whereas here you can see where the numbers are coming from. So that I would hold up as a demonstration of the advantage of using this group theory instead of just using angular momentum calculus by itself. Okay, so big difference. Okay. Okay. Now we're going to proceed with this, as I say in the next lecture. This is the whole darn octet matrix for all of the operators that we possibly have, which are E1, E12, 1,3, and so on. The little numbers up on each one of the matrix elements, it indicates who gave that entry. Okay? So these, you know, the usual things, square roots of 1 over the square root of 2, the square root of 3, and so forth, are all there. And of course the diagonal of this consists of 1s and 2s, and it would be 3s if we had a symmetry, but we can't have that for Pauli's rule. Okay, so I just want you to see this. This is the way you lay out a shell calculation if it can be fit on the board. The problem is the shells can get pretty complicated, and that's what I also want to show here. Okay, so we're just going to quickly go through the level diagrams that we're looking at here. So far we've worked a little bit with this guy and even less with this guy. Those are the two electrons in a P shell. But that's the fundamental one, the quark representation. If it was high energy physics, this is just plain old atomic physics of a P shell, lithium atom. Okay, so here goes the triangular representation, and then a bigger triangle right here for the sextet, totally symmetric, remember, and then there's the weird anti-symmetric. So we had a matrix today that had this as a basis and this together. We're now working on this one right here. This one will come later, especially when we have to put spin on the thing. And then the thing that I'm not going to be showing for the D shell and the F shell is the rest of the shell. And what happens is you get the same representations conjugated with tableaus that are the complement of the tableau next door here. This is talking about P with 4 electrons. And finally 5 electrons makes that weird thing. And its complement is just a fundamental. There's one box missing. Now when you finish the thing and make a vacuum, that's putting in the third box, totally paired up. Its physics disappears, basically. It becomes a spherical something or other. That's a closed shell. That's a rare atom. Helium, neon, all of the noble gases, okay, that don't react with anything unless they're totally beaten up. So I just wanted to show you the rest of the shell is a copy, but a funny kind of copy of the first part. But the middle of the shell is, of course, the one that has the most structure. So that's P2 and P3, and that's the level diagram there. And there's this thing called seniority, which I used to play a lot with, and I have yet to really make it work for me, so that's a whole nother story. Anyway, here's D squared, okay, and it's got this symmetric tableau and the anti-symmetric tableau. Now remember, the most anti-symmetric states have to be lowest in energy, because the more anti-symmetric the wave function is, the less the probability that any particle gets near any other one. The wave function is making nodes around being close. So if the electrons are put in a thing where they're magically kept away from each other, the electrostatic repulsion is greatly reduced. And hence you're low in energy. But when you start making it symmetric and come up and they're really fighting with each other, oh boy, really a lot of tension in there, that's the higher states, you say. Okay, so keep that in mind. So that's why the very lowest one, and it is a little, you're going to have to look on a higher resolution to see what all is written there. But just to give you an idea, the D shell starts to get complicated. It's already more complicated than that with D3. And it's clearly obvious. There's the tableau that we've been working with right there. And then, look what you got for D4. Wow, lots of levels. There's D5. That's the middle of the D shell right there. There's some comments on how the seniority, which is the number of unpaired electrons. Here we only have one pair that isn't paired up at the very top there. Okay, but you ain't seen nothing yet. F squared already is more complicated than our little exercise today. Okay, but F cubed, it goes up another order of magnitude. Here's our tableau that we worked on today. You put a 7 on this and you've got a lot of states in there. It's not just an octet anymore. It's a lot of states. And this one too, it's got a heck of a lot of states. That didn't even exist with the two thing. I take that back. It does exist for the P shell. But here's F4. Wow, it's getting heavy. Here's F5. Look at that. Now here at the bottom with very few states, and there is a pretty big gap for the next one. But this is what you see in the in serine, one of the actinides. You see mostly the lower stuff. And here is S6. We're almost at half shell, but look at all the states. It's just incredible. Each of them described by tableaus at first, and then some other groups that people use to try to make some sense out of the shell structure. This is a listing for that. For the D shell, they worked with R3, and then here, let's see if that was right. That's R2L plus 1, so L equal 2. That would be R5, rotation group in 5 dimensions. That's what defined this thing called seniority for the D shell, and then finally Q5. Okay. Well, this is R7 and U7, and then the exceptional D group gets to have a day in court. Not a very successful one, but still it gave a little bit of information about the F shell. That's a whole different area of group theory that really, it's one of those things I think that gave group theory a bad name, because it really didn't give us that much. We still have not made a complete accounting of this old Rocca scheme. This is what Rocca did. It spent his whole life practically doing before he taught Elman how to use U3. Okay, well that's about it for today. We already seen that diagram of a tableau, and here are the guys we worked with today. Okay, here, here, and here, and then here are those papers that we need to get onto the web. They're
I
somewhere.
have electronic copies.
You
The
actually
majority
do.
of them.
Yeah, because I don't even have.
Dr.
I
Hussar,
gave them all away.
I had to go overseas.
do you have a copy
Yeah.
of the first
Oh,
article
of course.
there?
Pardon?
Do you have a copy of the first article, Unitary Calculus for Electronic Orbitals?
Well, that's a book. It's about yay thick, and I do have a copy of it. And I guess we could scan that in.
Let me try for a copy first.
Okay.
It depends on the size of the volume whether I can get to it or not.
It's less than 100 pages.
I've got the whole handbook, so
Yeah. Right.
there's a good chance.
Yeah, it shouldn't be a space problem.
The only
Yeah.
one I couldn't find was my blasted addendum.
Oh. Huh.
When you go out there and try and find my corrections, it's
Okay,
like a
now
whole-
that's something that I should tell you. I put that addendum together in a nice fashion, scanned it in, and it should be up there.
Right, you covered us. But
Okay.
if you hadn't, we wouldn't
We'd
have
be
had
stuck,
any
yeah,
requirement.
right. Now, we're gonna need that when we get around to doing the molecules, nuclear spin properties, but that won't be for a few days.
Okay.
We're getting there.
And also on this, the page 2, the supplemental references, I'm going to go ahead and put Brad's paper in here for completeness.
Okay,
Which one? What?
sure.
Your latest paper, the one you sent me an email,
Which one's that?
I could pull it up. It's the one you sent me in the email. How many of them have you written? It was about the Molian series.
Oh, yeah. What's on the archive so you can link there? Brad probably.
Well,
needs-
whatever is the best link for it, we should
So
have.
when have you published it?
We should have it on the site.
I have a copy of it. It's
Okay,
already
yeah.
there, but I'm
Post it
just
on
getting
archive.
permission.
Yeah, it probably needs to be rewritten and
Yeah.
expanded.
Well, when you
That's
have a
what I'm
copy,
trying-
shoot it to me and I'll put it right out there for you.
Yeah.
Shoot me
And
your
of
most
course,
recent stuff.
this is a work in flux, so you'll be responsible for getting the latest to, you can show him how to put it up there, or else he can just give it
You can
to
just
TC
email.
and he can put it up there.
Yeah,
Keep it up to date. Yeah, the reason we'll do that.
that's part of the AMOP
Yeah,
series.
sure. Okay. All right. I guess we better put the video to bed here. And also